let's talk about three words we all think we know: work, energy, and power. You talk about a hard day's work, or feeling full of energy, or a really powerful car. But what do they actually mean in the world of physics? Well, the answers are super specific and, honestly, a little surprising. So, get this. You've got a weightlifter holding a massive weight straight over their head. Their muscles are burning, they're shaking, sweating, they are putting in a ton of effort, right? But if you ask a physicist, are they doing any work on that weight? The answer is complicated, and it gets right to the heart of what we're going to unravel today. And this is exactly where our everyday language and the language of physics part ways. For us, work is anything that feels like a struggle. Studying, thinking hard, you name it. But for physics, nope. The definition is way, way stricter. It's not about how tired you feel. It's about a force causing a very real, very measurable result. Okay, so let's get into the nitty-gritty. In physics, the idea of work has nothing to do with effort and everything to do with two simple ingredients: a force and a distance. Here's the deal. For work to happen, a force has to push or pull on an object, and that object has to actually move. It has to be displaced. The formula, W equals F d cosine theta, really nails this down. That cosine theta part is just a fancy way of saying we only care about the part of the force that's pointing in the exact same direction the object is moving. So you can see it right here. You've got your force, F, acting on something. And because of that force, the object moves a certain distance, d. Work is just the measurement of how much that force actually contributed to that movement. If you're pulling a wagon with a rope at an angle, only the part of your pull that's parallel to the ground is actually doing the work.
And this brings us right back to our weightlifter. They are applying a massive upward force, right? But is the weight moving? No, the displacement is zero. So since d equals 0 in our formula, the work done on the weight is also 0. It's the same reason pushing against a brick wall does no work on the wall. Lots of force, zero movement, zero work.
So if doing work on something makes it move, what does that motion really mean in physics terms? Well, it means you've transferred energy to it, specifically the energy that an object has because it's moving. And we call this kinetic energy. Anything that moves has it. The formula is K equals 1/2 mv squared. Now, it depends on the mass, sure, but look at the velocity term. It's squared. That's huge. It means if you double an object's speed, you don't get double the kinetic energy. You get 4 times the kinetic energy.
All right, so we've got work, a force causing movement, and we've got kinetic energy, the energy of that movement. You're probably thinking these two have to be connected, right? And you are absolutely correct. Physics links them together with this really beautiful, really elegant idea.
And this is it, the work-energy theorem. It's so simple, but it's incredibly powerful. It just says that the amount of work you do on an object is exactly equal to the change in its kinetic energy. So if you do positive work, like pushing a car to get it started, you add kinetic energy, and it speeds up. If you do negative work, you take kinetic energy away, and it slows down. It's that direct. Let's make this real. Imagine a cyclist coasting along. They've got a bunch of kinetic energy. Then they slam on the brakes. Now, the force of friction from the road is pushing against their direction of motion. That means friction is doing negative work. And what does that negative work do? It literally drains the kinetic energy right out of the bike until it hits 0, and the bike stops. But energy isn't just about things that are already moving. What about the energy that's just waiting? That's stored up, ready to go. This is where we get into the whole idea of potential energy. I love this definition because that's exactly what it is. It's the energy of possibility. Think about a stretched rubber band, or water held back by a dam, or a compressed spring. It's energy that an object has just because of where it is or how it's shaped. And here's the magic. In a lot of systems, energy isn't really lost. It just changes its costume. It morphs from kinetic energy, which we call K, into potential energy, we'll call V, and then right back again. But the key is, if you add them together, that total amount of energy stays the same. It is constant. This is one of the most fundamental laws in the universe. The classic example, of course, is a falling ball. So imagine a ball just sitting at the edge of a cliff. It's not moving, so its kinetic energy is 0. But because it's so high up, it's packed with a ton of stored gravitational potential energy. This chart just shows that transformation perfectly. Look, at the top, it's 100% potential energy. As it starts to fall, that height gets smaller, so potential energy gets converted into kinetic energy, and the ball speeds up. Halfway down, it's a perfect 50-50 split. And right before it smacks into the ground, all of that potential energy it started with has turned into the energy of motion. But the total energy at every single point along the way is exactly the same. And remember, potential energy isn't just about how high something is. A spring, for instance, stores potential energy whether you stretch it out or you squash it down. Either way, you're loading it up with energy that's just bursting to be released. And this graph shows that exchange so well. It's like a dance. The blue line is potential energy, the green is kinetic. As one goes up, the other comes down, back and forth in this perfect rhythm. But look at that red line on top, the total energy. It's perfectly flat. It doesn't change. It's just a constant, beautiful trade-off between stored energy and moving energy. Okay, so we've got work and we've got energy. There's just one last piece of the puzzle, and that's power. Because let's be honest, in the real world, it's not just about whether you can do the work, it's about how fast you can do it. Power is just the rate of doing work. Think about it this way. Walking up a flight of stairs and running up that same flight of stairs requires the exact same amount of work, right? You're lifting the same body against gravity over the same distance. But running requires way more power because you're doing all that work in a much shorter amount of time. The unit of power is the watt, named for James Watt, the guy who basically perfected the steam engine. And just to give you a feel for it, 1 horsepower, a term we still see slapped on the side of engines, is equal to about 746 watts. It's a direct line from the Industrial Revolution right to the physics we're talking about today.
So let's just wrap this all up. In physics, work needs a force that actually makes something move. Doing that work changes an object's kinetic energy. In a perfect little system, that energy just bounces back and forth between kinetic and potential, but the total amount never changes. And finally, power is just how fast you can get all of that work done.
But that leaves us with one last, really interesting question. We've been talking about these nice, clean, conservative systems where energy just changes form. But what about messy forces like friction? We saw that it did negative work on the cyclist. It took away kinetic energy. But that energy didn't turn into potential energy. So where did it go? That's a great question for another time. Thanks for watching.